Integration to find the area under the curve does not look fun at all. Look at all these mind-boggling curves covering areas which looks as if it's going to take an eternity to find. How could anyone like a topic like this?
Try to think instead of a shelter in our everyday lives. A shelter, no matter where you see it, always comprises of a roof, a floor, and two walls when viewed in two dimensions. This will be the basic principle for integrating area under a curve. Because when mapped against integration, the roof matches with the top curve, the floor tallies with the bottom curve, and the two walls correspond with the lower and upper limits. I'll show you several examples of how easy it is to apply this technique. Let's start with something simple, the area bounded between an exponential curve and a horizontal line from x equals to 0 to x equals to 2. With some imagination, notice how this shape resembles the area formed by an architectural form, with a roof equation of e to the power of negative 2x and the floor equation of negative 0.2 when expressed in terms of x, and two vertical walls of 0 and 2. This is a straightforward integration of e to the power of negative 2x minus negative 0.2. If done correctly, returns an area value of 1.66 square units. GeoGebra shows the illustration of the integrated area value above the x-axis, but as seen from the animation here, the described area tallies perfectly when the roof and floor are shifted up by the same magnitude. Now for something a bit more complex, how to calculate the bounded area formed by several curves. Not a problem. In this example, the area bounded between the x-axis and the two lines can be envisioned as a tent pitched around a campfire. Now, a tent has no walls, but it is pegged to the ground, also known as the x-axis, so you'll have to do some algebra here to find the x-intercepts. In this case, they work out to be negative 2 and 10 over 3. The integration here will have to be done over two sums, from wall 1 to wall 2 for the upward sloping line. The tent pole in the middle is represented by x equals to 2/3, and from wall 2 to wall 3 for the downward sloping line. Eventually, add them up to find the area under both curves. I call the next situation the time saver based on the amount of grief you save. Observe the area bounded between a line and curve below the x-axis. The conventional method requires you to find the intersection points. Naturally, these serve as your upper and lower limits. From there, you find the area of the yellow trapezium. Then, you find the area between the x-axis and the curve. Finally, you subtract the difference for a value of 2.61 square units. Picture an igloo being turned over. It's still a shelter, isn't it? The igloo base now resembles a roof, and the dome roof is now the floor. The intersection points are the walls. I now only need to integrate once. In the process, grouping like curves to save even more time to obtain the same outcome of 2.61 square units. The last case is mind-blowing in its simplicity. This time, the area is bounded by the curve, the y-axis, and two horizontal lines. However, the concept remains the same. Imagine a building tilted on its side, still forming a shelter with a roof, floor, and two walls. Now that our focus is on the y-axis, everything is in terms of y. So, an exponential curve must be represented with x as the subject of the equation. We manipulate it into its logarithmic form, x equals to negative half ln y. The floor in this case is x equals 0, and the two walls are 0.2 and 0.6. Instead of finding multiple areas to subtract, one integration is sufficient. To summarize, the skills discussed today involve visualizing a two-dimensional shelter with one roof, one floor, and two walls. This simplifies the integral into a straightforward problem, and a tedious portion, if any, is spent on simultaneous equations to derive intersection points for the values of both walls. With this hack up your sleeve, hopefully you won't be caught off guard when dealing with integration ever again.